I'm very excited to have Vish today. I'll give a very short intro for everybody, but Vishwadeep Deo is a senior associate and facade designer at Front Inc. Front, for those of you who don't know, is a world-renowned facade specialist organization that brings a cross-disciplinary collective approach of architects and engineers together. Vish has more than 18 years of construction industry experience and has been lead design on a number of projects, lead facade design from cultural, institutional, transit, residential, all over the world, North America, Europe, Asia, everywhere. I'll name just one or two here, but there's a long list of projects that he's been involved with. So a couple, the Ronald O. Perlman Performing Arts Center, the World Trade in New York, Google campus in Mountain View, with Big and Heatherwick Studios as the architects. He worked on Barclays Arena in Brooklyn, as well as Mercedes-Benz Futures Laboratory and Museum in Stuttgart in Germany. Before Front, Vish worked at the Digital Design Group at SOM and the Digital Fabrication Lab at Georgia Institute of Technology in Atlanta. And Vish combines practice with teaching. He's taught with my studio, and I've been very, very lucky to have him for the last 3-4 years. He is also consults at the University of Tulane. But that's the quick intro for Vish. I hope everybody is as excited, or even just half as excited as I am for this. That will be a sufficient amount of excitement, I think, for this lecture. But I'll let Vish take it away here.
Thanks, Daniel. And thank you for just inviting me for this master lecture. It's a great privilege to be here at the School of Design and then talking to you guys and the students and beyond. I know some people are actually calling in from India, so I'm really grateful for that. So if everybody is ready, we can key in and then get the bus rolling. As a starting point, I wanted to sort of let me see if my slide progresses further. Yep. I wanted to throw this image up in case anybody was missing air travel. This is a cross section of Airbus A320, and the reason why it's there, and just so we understand what this interface is really telling us. What I understand as this cross section to be is a layering system with different materials, when they overlaid on top of each other, create a composite sort of an interface between the natural world outside and all the forces that are acting on it and the human space inside. And how they negotiate between the two worlds is through this skin. And the way we understand it, this skin is driven purely by its efficiency. And that is the constant factor of actually what drives this efficiency forward. For the longest time, I think aluminum alloys were being used to craft most of the airplane industry. But in the recent, some of the recent trends has been that they're starting to use a little bit more carbon fiber reinforced plastic. And the reason of why that is happening is it's just pure efficiency of strength versus weight. If we compare that to our industry, the building industry, where we are in the business of building buildings, the efficiency is paramount. We care about strength to weight ratio. We care about how the air moves around the building. But the single most important driver of innovation in materials and system has been, and for the longest time will be, the architectural design intent. And that's one key sort of parameter that I wanted to kind of stress on. is the single most important driver, at least from a facade design and engineering standpoint. What pushes the boundary has been the creative minds of the architects, which would be you guys. Um, for this particular presentation, I wanted to kind of sort of select and use three different materials, very simple, very straightforward, we know them, but used in a slightly unconventional manner. And just to understand why we are using it, how it's sort of a story of these three materials for these three projects, um, just to track why it was important and how the design intent from the design studio sort of distilled the selection of the material and how we processed it further to the actual realization. Of the three projects, one has been built, one is unbuilt, and the third one is currently under construction. Starting with the acrylic, the project is Park Avenue Plaza in Midtown Manhattan. It's a public arcade. It's a through block, sort of an interior condition. And it was a very sort of a unique project for us because we typically work on the design and engineering of the facade, but this was completely interiors. And what it had was it's a building that was designed originally by SOM in 1980s, and it is the public plaza was definitely used to a large extent, but it was definitely in need for some renovation. So Jansen Goldstein were the design architects who were called in by the client Fisher Brothers and Jansen Goldstein, and their recommendation, because we had worked with them previously, requested us to join them as glass and acrylic consultants. This was the first brush of what they imagined the space could be. They wanted to not only have a band of opaque glass wall, which was purely a cladding onto an opaque wall, which had these vertical tubes that were infilled with acrylic light fixtures. But the topic of this particular presentation will focus primarily on these 8 columns. They were very clear shear columns, purely used as an organizational tool and a decorative element. They were not structural. And it was very critical to translate this design vision into an actual construction of this particular piece. Just because I think there were a lot of drivers that actually drove this particular design concept. One, not only organizational, but it needed to be as transparent as possible. Something that is governing the city planning code requires all arcades to have, and so as to minimize any sort of visual obstruction. So the decision needed to be made. These were about 30.5 feet tall acrylic columns or any clear columns. And our sort of starting point was, what material should we make it out of? Two options were glass and acrylic. Both of them, I think we had sufficient experience, more of glass than acrylic. After working on Jane's Carousel in Brooklyn, we understood the material. We knew what it could do. We knew its benefits and drawbacks. So we started to take that forward and try to understand and really distill through what that material could be. So we brought forward the criteria that could define for us what this material is. We looked at its weight, we looked at its clarity, how it can be fabricated, how it can be installed in that space, what sort of maintenance does it require, and does it meet the fire code, because it was critical because it was an interior space. As usual for any other project, we definitely went face down, deep dive into the detailing and really sort of started to draw these details out, keeping in mind what these contexts were. On the left top corner, you could see the laminated glass version. That's how we would have built it if it was out of glass. And on the right was pure acrylic. We also looked at reducing the weight of the glass, because for us the biggest constraint for the glass was not only how we could fabricate with these multiple sort of laminate plies, but also the weight. Just to have the logistic to actually erect 30 feet tall columns, which are about 5,000 pounds heavy, would have been a tall order. So we started to excavate the material out of these columns with the keeping in mind this was glass, and tried to figure out how we can actually build it. Uh, Quickly we realized, I think, not only the weight was acting against us, the glass with the multiple laminates and interlayers, and the edge treatment was not as clear as we would have wanted. The fabrication of those multiple plies at 32 feet length would have been also pretty tough. Installation required would have been a special jig that would have to be installed in place to actually install these columns in. Maintenance wise, actually the glass was actually better. For acrylic, it tends to get some scratches, but it can easily be maintained. What we faced an uphill battle for with the acrylic was its fire code. We knew that acrylic, being a plastic, definitely was not a non-combustible material. It had a lower performances compared to glass when we speak about fire performance. Cost also was much lower, or slightly lower at least, for the acrylic. So for us to address and sort of install material, our sort of task was straightforward. We need to address the fire issue. We teamed up with Arab's fire department, and they sort of collaborated with us to sort of go through and distill it down, what it really means to use acrylic. They looked at code, and we were able to, just because it was non-structural, we were able to define it as a decorative element. And for a decorative element, according to 2008 code, it needed to be class CC2. And we tested it, and based on our testing, it was actually CC1 and CC2 criteria was applicable to acrylic. So for us to classify that material as class CC2 was critical. And we actually were able to get there, and we did it. And I think that was a testing that was then brought forward in front of New York City Building Department. I think everything went okay, and they approved it. Once was a system design of how are we actually attaching and supporting these acrylic columns. In addition to that, I think they also required special sprinkler heads just adjacent to the acrylic. No combustible material in the lobby, no furniture with any sort of higher burn characteristics were allowed. So everything is metal, non-combustible around these guys. There's only one source of fire or heat. That was a Starbucks kiosk, which was stationed at a certain distance. And based on fire separation, we had that as well. The requirement from a system standpoint from buildings department was to not, in case of fire, we expected the base of the acrylic column to start getting affected earlier than the top. So there will be a case where if you're just base supporting it and the top is just a lateral support, it might actually slip down and fall to the ground and might affect occupancy safety. So what they wanted us to do is to figure out a solution to reduce the base getting compromised. So we came up with a system where we actually allow the vertically slipped connection at the top, but also have these sort of nodes or sort of tabs that actually allow it to be top hung if the base is compromised. And once we got that clearance, we got the CCD1 code clearance from the building department. I think after that, I think we were just off to the races. We went through the normal bid and bid process and the supplier qualifications. And ultimately, the production of these acrylic columns went to Reynolds Polymer out of Grand Junction in Colorado. These are some images from the fabrication. Most of these acrylic columns are first machined using a 3-axis CNC router. Then they are polished and cleaned. Then the tabs are added in a sort of a large oven using a chemical bonding agent. And under pressure and heat, it bonds to these acrylic columns. And after that, it is all polished together. Any sort of defects are worked away with a cement grinding agent. Uh, these tabs are then actually we were able to undertake a factory inspection for general QC purposes. We checked the actual tolerances of these columns. We looked at their thicknesses. We looked at, we were able to empirically hang these columns using those tabs and actually test those tabs out. Are they able to take the load or not? I think we hung them for quite a while and it was sufficiently stable. There was no effect and the bonding agents worked perfectly. We were also able to look at the clarity and just to understand going from sort of pure rendering to actually this. For us, it was pretty convincing. I think it was very clear. There were some optical distortions at the edges, but otherwise it was super clear, as you can see in the images. These are some images from the actual installation in the lobby. The columns are brought in place and they are hung up on the right-hand side. Just a reminder before we close this chapter, this is where we started. This was the intent to have these sort of very clear shear columns in place. And following few images are how it is right now built. In the background there, you could see the gray ceramic frit glass with the glass tubes. I think that would be a topic of another discussion. Those were pretty special as well. But in terms of achieving what the design intent was, just to add value to this place, I think acrylic worked perfectly. And all the hoops that we had to sort of go through to actually make it possible seemed worthwhile. All right, on to the next station. This is steel, another well-known material, but used in a slightly unconventional manner. This is a project not far from UPenn. This is just outside of Philadelphia in one of the suburbs. This is a project that a friend had worked on previously. It's a private residence and the owner actually owns a private gallery as well. So the bottom part of this picture, just below the red bar, is that gallery the friend had worked on and helped with the fabrication a few years before this project. This is that gallery. And the connection that you see here is from the residence to the private gallery there. And this is the site of this project. When we were brought onto this project by Point B Studio, who you may know, he's a Philadelphia regular. This was the initial sort of cut on what he had envisioned. Speaking of John Shields, this was a connecting piece. It was sort of imagined to be an extension of the gallery. So when you enter from the residence side on the left, go towards the gallery, this seemed to be, this should appear and behave exactly like an extension to the gallery. So it needed to be super clear at the base, but very sort of, and the client was driving this process and is one of those guys who really wanted to see something special here. So we jumped in and we started to look around and there were a few constraints that we actually had to navigate through to actually make this. This is where we stopped the project. This is currently, the status of this is unbuilt, but the progress from here to here sort of gives you a little picture of what went into realizing, or at least to a point where it could have been realized. An interior view of the bridge. So Speaking of constraints, we were faced with extremely short timeline. We had to sort of go from design boards to execution in quick time. We understood from the architectural design intent that the design surface that actually governs the geometry, we do not want to change that, or at least not to a large extent. Some optimization were possible, but changing the geometry was not, because it was critical why the ground plane itself is a sort of a environmentally sensitive site, and we wanted to touch on that site at a very specific location and not anywhere else. In general, we were looking at a free-form geometry, so whatever system that we could actually envision test should be compatible with a free-form geometry. Uh, the whole system needed to be as close to as possible to a continuous surface. Um, there was limited site access. So whatever means we actually define the system, it needed to be easily transportable to the site. Um, we should also keep in mind that the residents will be actively used, so no heavy machinery were allowed or were to be allowed during the execution of this project. We understood we had access to CNC fabrication, but there was no milling process. So those were the limitations that we were working with. And after deliberations and future reds, we sort of arrived at this concept of steel sheet voxels. So three-dimensional voxels made out of steel sheet. This was a starting geometry. This was one continuous surface which touched down on either side, one side on one and two sides on the other. So it was sort of a three-sided tripod surface connecting the residents to the gallery. We started discussing it. How do we actually skin this? What sort of structural system should we use? We obviously went, first step was the most straightforward, to use a UV division of the surface to arrive at a grid shell. We looked at digrid. Then we arrived at circle packing and sort of an approximated polygon mesh. And this seemed interesting, a lot more texture, a lot more character. It sort of fit a lot of bills. Then it came down to how do we actually execute, or what is it exactly if we do actually panelize it like that. Um, these are the image here sort of indicates the three big components. You have the base bridge, you have the top and roof structure, and you have the inclined insulated glazing. And after further deliberation, we went back and forth, and the general thought process was the image on the left is a texture that is interesting, and point B wanted to sort of delve a little deep into that, see how we can actually sort of extract that texture and sort of imply or apply it onto the surface. And the image on the right is from front, and we sort of started to look at it in detail. It was sort of a vignette of that system, and see if we can actually bring it close. And I think the image on the right sort of convinced them, the design team at point B, that this seems correct. And the image on the right stayed till the end as the preferred sort of approach onto the system. To go back and look at the actual geometry, just a layering of it from exterior to interior, there was some thought of, I think the most of the thought process on the exterior tiles was sort of much in play, but we were looking at some sort of an exterior tile with waterproofing and insulation underneath that, and on top of the structural voxels. There was these additional sort of pieces, sort of a honeycombs cavity zones inside called the visual voxels, we were calling them. Sort of a finishing interior finish applied to the underside of this surface. In addition to that, there will be inclined glazing on either side, regular insulated glazing units, base supported, top support with no framing, and then at the base was the slab. detail of how things would come together. This is cut sort of in a transverse section, looking at the exterior, going through the waterproofing insulation, the structural voxel, and the inclined glazing at the base. The key part of it was most of our work revolved around analyzing it structurally, what it would mean, this aggregate that we are creating, how do we analyze it, how do we understand it. As you can see from the geometry, it sort of is somewhere between a portal frame and a shell structure. And it sort of existed between these two structural diagrams. We understood the shell behavior. We understood how what happens when it is compressed. There's what are the failure mechanisms, and how do you control it? For instance, in compression, you would see some buckling, and you can control it by reducing the actual cell radius. In tension, you would see separation of the fasteners that are connecting these voxels together. And we could improve it by improving the load transfer between the cells. As far as bending is concerned, we could control it by increasing the depth. So those were sort of the building blocks of what this structural diagram could imply for the voxel aggregation that we are creating. Looking at compression a little bit more, when you do compress it, the voxels made out of sheet metal would undergo plate buckling. And based on our analysis, we were able to sort of define what that plate buckling could be for each of these voxels. And at these hot zones where we were seeing a higher concentration of buckling forces, we were sort of developing a script that could automatically address that by one or two ways. Either by subdividing the mesh further, reducing this radius of the cell and increasing the buckling capacity for each of these cells. This is after subdivision. And then to go back here, the main question was how do we actually generate the initial, we understood the sort of the buckling concept, we understood the shell performance under the loads and the failure modes. But how do we generate a map of these voxels and what should the logic be? We looked at meshes, and that's how we were going to progress on these surfaces. There was a starting surface, which was a pure surface coming from the architects. And then we were converting that to a triangulated mesh. And then using that mesh, we deployed circle packing techniques. And once we had that circle packing, we were able to adjust the mesh and relax the mesh to arrive at a polygon which was reasonable based on certain rules. All along when we were developing these geometries, the basic mesh data structure was were kept intact. Obviously, the cell and the vertices, and also the chords. The exact mesh that was getting generated based on that analysis was imported directly into a finite element modeling software through a localized plugin that Front had developed. Again, some of the basic sort of data structure that we sort of understand a particular mesh to have. You have the concept of half edges, which is a shared edge. You have the face, the vertex, and sort of the concept of next chord. And using some of the mesh manipulation techniques, we could analyze which elements were too long, and we can actually implement flipping, for instance, to reduce that length. We can also look at subdivision, like what you had mentioned previously. So when we had that initial surface, the first step was to analyze it for compressive forces. We just took it into strand and then analyze it, assuming it's a small thin shell concrete, and just to create a map of compressive forces. And these compressive force map actually drove the cell aggregation that you see in the bottom. So the cells were smaller where the compressive forces were higher, and these were all auto-generated based on the loading map diagram. Going from the cell geometry, we basically manipulated the depth of these cells as well. And these are some of the permutations that were generated from the script based on different input parameters. Speaking of tension, the acting forces on the fasteners as a cause of splitting, we looked at how we can actually create an easy transfer of load between two cells, and we looked at actually welding, spot welding some of these elements. Looking at bending again, as previously noted, I think the bending forces are effectively sort of controlled by increasing the depth. So the other element or the rule that was embedded within the script was to increase the depth of these voxels based on where we saw maximum bending moment. And there was a bending moment map, and it actually corresponded to the depth of what these voxels were designed for. So higher bending moment implied deeper voxels. Lower bending moment were a little shallower cells, and the vertex-based offset allows shell thickness to vary as well. We could go and manually change some of these elements if you wanted to. Based on the initial geometry, subdivision, circle packing, and subdivision of the polygons, the resulting geometry is a two-dimensionally curved surface, which could be issue if you're just dealing with straightforward sheet fabrication. So we needed to undergo a little bit more rationalization of the geometry. And going from the left image here to the right, it basically created certain offsets between each cell as each of these surfaces were rationalized as a planar geometry. Once these voxels or three-dimensional cells were generated in the computer software, we understood that they were based on the the bending moment diagrams. They were the depth of each of the cell was based on the bending moment. The circle packing was based on the actual loading map of a concrete shell. But we wanted to bring that final model back in and actually look at it and analyze it as a separate second engineering process. There were two types of models that were generated. One was discrete and one was continuous. The discrete model was primarily used to check fastener sizes and compute deflections. And the continuous model was to analyze the buckling forces. This is the grouping of individual discrete voxels. Some of the fasteners being modeled. And using the model, I think we were able to sort of zero in on each and every fastener and what the type of force or the actual quantity of force that is acting on each of the fasteners. We could see which were getting to the high, which were actually getting overstressed. So we could address them or increase particular cells. The allowed us to look at the buckling forces, how the loads were getting transferred between the cells, which were, are you guys able to hear me?
Yeah, we can still hear you. It's a little choppy, but we can hear you.
Okay. So the continuous model allowed us to look at buckling forces specifically. And what it did was to generate a load map, again, based on these sort of buckling forces that allowed us to sort of zero in on each and every cell that was actually exceeding the limit of those forces. We did some back-end calculation to arrive at the buckling constants, which were not available, obviously, for the sort of a bespoke system. Um, that allowed us to sort of generate these buckling force maps and allowed us to identify and the hotspots as far as the buckling forces are concerned. And what it did was it allowed us to isolate those cells in particular and sort of call out those cells for additional reinforcement, either increasing the gauge of those sheet metal or having some sort of additional sort of reinforcement at those cells. Where we left the process, where the client sort of decided to hit a pause button on, we were sort of starting at the next phase of iteration. The intent was to sort of start to see how we can integrate some of the systems into these cells. We were looking at air distribution system through these voxels, how they can all be sort of exist together in the skin activated system. So very much like a monocoque system for the Airbus 320. All the systems were integrated into the skin of this particular project. Just a recap where we were and what are the steps that we followed. There was an initial design surface. We took it to finite element analysis to actually analyze and sort of map out the results from there for compressive forces. That allowed us to generate a circle packing mesh and create a hexagonal polygon mesh on top of that surface. Then we sort of analyzed the bending moments, and that input provided the depth of each of those cells. And then once those cells were generated, they underwent one round of rationalization for planarity of those surfaces. And those surfaces were then brought back into the structural analysis software to analyze it in a discrete fashion and a continuous fashion for final validation and check on the fastness. All during the course of this exercise, Front has also, we started using a suite called Front, which is a sort of a custom Grasshopper component that Front has developed, which does few things for us as far as facade design engineering is concerned. What it specifically does is it embeds the geometry with a lot of information that you can extract and use it the way we want to. The other sort of benefit or feature that we sort of embedded in that component is auto drawing generation. That allowed us to generate each and every sort of component automatically and also tag it within unique ID. These are some of the pieces. We looked at auto nesting on a sheet as well, and all the parts getting generated. Some of the construction images of a mock-up. This was all done in-house at Point B studio. Rivets being used as fasteners. So you could see to bend these plates, there were cuts being made intermittently that allowed it to be folded. you could see because of the planarity of the surface, there's a slight deviation from the adjacent cell, and that's what you're seeing here. Some concepts being tested for the interior finish or the visual voxel or interior voxels, as they were called. All right. So we are going on to the third project. For this, we are going back to New York. And we are at the World Trade Center site. This is the last parcel that is getting developed after 9/11. Master plan was approved. This is the Performing Arts Center that has changed hands over the time. For us, it has been a long process, but the actual process has been much longer. In 2001, as we know, LMDC was formed to redevelop the 9/11 site. Studio Libeskind sort of got the competition to actually do the master planning, and this Performing Arts Center was part of that master plan. Gary Partners were awarded initially with Snowhead, I believe, to design the Performing Arts Center. The top right image is from Frank Gary's office and their proposal for that particular project. As the main sort of caretaker of the Performing Arts Center changed hands, there was a switch in the way they wanted to take this Performing Arts Center design to. They floated a new design competition, and Rex were invited in 2014. And Rex invited Front to join them in the design competition for this particular project. So our sort of involvement started in 2014. It's been almost 7 years. It's been a long process, but I think we have made a lot of progress on this. Front sort of after getting the invitation and working through that invitation cycle for 1 year, we won the competition. And then we had to reapply to be the facade consultant because there was no automatic sort of induction of all the competition participants as the actual consultants for the project. So we had to reapply, undergo the actual interview process, and we got selected for this particular project to be the facade consultants. Currently, the project is slated to open in 2023. The way this project was conceptualized in Joshua Remus's sort of initial sort of description was that of a mystery box. The intent from the Performing Arts Center team and also Rex's team was to create something very unique that sort of leads a user to different experiences and always sort of surprise them at each and every corner. So that was sort of the intent, and the way it was developed as a very forward-looking and a modern and contemporary performing arts space for theater, dance, film, and sort of really experimental art form that can happen in this space. One of the key drivers why this was called the mystery box was it's a collection of 3 or 4, I believe 4, with one of the performing spaces being a rehearsal space that could develop as a performance space, could actually be combined with each other in several different configurations to create a performance space of different sizes. And that was, I think, one of the main sort of invention of this particular device that Rex has sort of thought of, is this recombination and combination of different performance spaces in different configuration that is allowed within this space. As far as the topology and the sort of the geometry of the volume is concerned. It was driven by two things, its particular context and the way it faces the 9/11 memorial. It needed to be a little bit somber, in the sense be respectful to where it is actually sitting, but also very practical, because as we know in New York, there's no bedrock under this building. That's like a maze of different structural systems running havoc. So there were only few selected points where the structure can actually touch down, and the way it sat on the infrastructure below, this sort of a geometry and the shape actually became very compatible with that touchdown points. So it worked both ways as far as the overall geometry is concerned. Um, the actual building itself, I believe, would be another topic of presentation, but I think we would want to focus on the facade of this particular project and how a material sort of started this whole sort of conceptualization of this facade and where we are today. This is a recent rendering, and this is not just a rendering. The stone texture and the veins that we see on the building are actual scans of the stone tiles that are being sort of being fabricated now, and this has been made part of the visualization for this particular project. This transformation is the most critical property that actually started the project. One of the key aspects of it was to figure out a material, in this case a stone, that could transform with light transmission. It needed to be translucent, it needed to change, it needed that sort of almost a phase change from daytime front lit and nighttime backlit. But the backlit also happens during daytime, looking from inside towards outside with the direct sunlight acting on it. So it needed that sort of a transformative quality, and then a definite texture of the veins itself. That sort of led a worldwide hunt for the perfect stone that we can actually find. Credit goes to Rex in that sense. I think they had a well-defined set of criteria where they wanted to be with this particular project, and specifically with the stone. For us to sort of imagine this really age-old material in a new highly efficient facade system, we needed to incorporate this stone into a curtain wall system. And for that, we understood there would be few steps that we would need to take to actually get there. Starting with the stone, we understood the stone would need to be of a certain quality. But then once we know what that stone is, what those qualities are, what thicknesses are there, we would then laminate that stone to glass to create a composite stone glass laminate. Then that stone glass laminate would then be incorporated into an insulated glazing. And that insulated glazing would receive all the curtain wall subframing and the cassettes and mullions as required to be able to hang it onto the building. We were not starting from scratch, at least from the use of a translucent stone material is concerned. Binary library is a well-known precedent. So is the Pious Church in Megen, Switzerland. But having these two precedents didn't really give us any sort of a concrete stone to go to. When we sort of investigated binary libraries, marble, they came from Vermont, and when we went to check on that, the stone that the quarry sort of provided as being used in this library was totally different than what this library actually has. There was some literature on what the stone is when we investigated that stone out of Vermont quarry again. That was completely different. So there was no stone. If it was, it could have been sort of a poetic, sort of a realization of retouching an American stone back again and reincarnating it into a new facade system. But we couldn't find the stone, but we knew what qualities we were looking at. And one of the key sort of drivers for us to search the stone type was its translucency. Translucency. It needed to turn to amber or gold color when exposed to light. The contrast of the veins were required to be higher because they wanted to sort of convey this texture that they had and imagine onto the facade. Uh, the thickness, sometimes when we backlit stone, specifically translucent stone, depending on the thickness, you are able to see the different layers that are being created within that stone layer. Uh, the stone needed to have a range in vein density to actually carry the concept through. If it was a uniform stone with a uniform vein, it wouldn't have worked. The vein needed to be directional to actually create a dynamism across the facade as we look up. Uh, some practical concerns were there because of cost. We wanted to reduce the wastage, how we can actually reduce the wastage. Uh, we needed to keep that in mind. We knew we are dealing with either marble for most part, or it could have been an onyx, or it could have been a quartzite. Quartzite is a pretty hard stone, but we knew marble is a soft stone, and we needed to figure out the right thickness and parameters to actually handle it properly. Uh, all these criteria sort of gave us indication of what stone types or the group of stones that we should be looking at. Uh, that particular stone type would then define what panel size that we can get it at. Granite comes at a larger sheet than marble because of its softness. Particular panel thicknesses, the way the blocks of stones are cut into slabs, there's a certain thickness that is more economical than the other. What is that thickness? Can we use that in a lamination process, or do we need to re-engineer that thickness? Can we re-engineer that thickness because these sort of cuts from the blocks to the stone slabs are dependent on the sort of heavy machinery that the quarries have. Um, what is the stone fabrication process? Additional stone fabrication process that would be required to carry it to the next stage of lamination. What are the stone testings we would do? So all these elements are embedded in this sort of selection criteria, and that's how we went ahead with it. Um, this particular presentation, I think you will see that there is not as much technical information here because of NDAs and so on and so forth. So the purpose, the way I wanted to sort of convey is the sort of the granularity of our investigations into the stone and the other processes and how this whole sort of the design process going from the material sort of design intent and folded into what's being constructed now. So there was a little lack of information, so I apologize for that, but I think our clients would be very happy. Uh, one of the components of actually selecting this particular stone was how do you analyze the vein and the coloration of the stone. Um, this was mostly managed by Rex, but they devised a sort of a filtering sort of a software tool that analyzed the bitmap of each stone and sort of uh, using the scanned images of the slab arrived at where they can cut to create a tile. And once they cut the tile, they can actually effectively tag that tile with how much density of vein it actually has. So going from the lower left image, they were then sort of able to define where they can cut to get 42% density where they can cut to get 14% density. On the right is sort of a bitmap where they had started the process with. So this is the image that they were working with. They took an abstract bitmap to the quarry, and it's like, this is what they want to do. And the quarry sort of responded that there's a range, but obviously material and being a natural material, there is no way to actually define what to recreate this bitmap in its entirety and its precision. So they wanted to define zones of heavy veining, medium veining, and light veining. That would then sort of give an indication to the quarry how much of the heavy veining stone is required, medium and light, and so on and so forth. What the facade contractors who are Gartner, which is part of the Lisa group, they did, it was pretty impressive in the sense that they sort of devised a tool that scanned the images of the stone and then created a database with its properties. And using those property tags, the software automatically populates a facade based on this bitmap and overlays it to its closest match, which is then being provided to Rex for further review, changes, or complete rejection if required. So that's sort of an automated process that are actually helping a lot. Currently, I think we'll go through that sort of the entire process in a bit. But just to circle back on the transformative quality that we were going for, this sort of image actually gives you that indication of what you're looking at. So sort of front lit, opaque, monolith, and then when the light actually acts on it, it transforms. As far as, so going one step more than just the stone, we as a team, had some experience working with stone and glass in a composite fashion. We had worked on the King Abdullah University of Science and Technology in Jeddah, which used a marble with glass as the rain screen system on the outside. We also worked on LVMH in Osaka, which used an onyx from Pakistan as a sandwiched material onto the backlit facade. So both of these were valid projects. Osaka more so because of the climate zone that it is in. It is somewhat similar to New York City. So based on that experience, we started to look at what would be the criteria for the laminate itself. We knew what the stone needed to be. What is the laminate needs to be? It needs to be compatible with the stone. The interlayer that we are using to bond the glass to the stone needed to be hydrophobic because we understood marble absorbs moisture. And if there is moisture within the laminate, it actually will create issues for lamination. So we needed an interlayer that is hydrophobic, interlayer that is as much color neutral as possible. We needed edge protection in the lamination design. We needed to understand the glass color. We were going for low iron, but also within low iron, you understand there is a range and some color variation within that. So we wanted to understand what is the most neutral low iron that we can get. This lamination needed to be resistant to high heat exposure and high humidity exposure for practical purposes. And also we wanted this exterior laminate to reduce the reflection on the outside. When we started this process of creating this facade from the initial design intent rendering, the idea was it needed to be as stone-like as possible. But when we put the stone between two pieces of glass, the natural reflectivity of glass gives it away. We wanted to cut down on that reflection. So we added a glass treatment, which is acid etching, very fine acid etching to actually cut down on that reflection. And when we see that glass laminate from the outside, the reflections have gone down quite substantially to actually make it look almost glass from stone from a distance. What this selection criteria allowed us to zero in was the glass type, the interlayer type, edge protection, the edge color. When I say edge color, it is the coloration of the edge capture and also any sort of masking ceramic fret that we are actually putting in front. Glass treatment, like I said, the acid etching on top, and also what sort of testing we would need. So there is a batch of testing we needed for the stone. There's a batch of testing we needed for the laminate itself. So going one step further from the laminate, now we are in the insulated glazing zone where this laminated composite is becoming part of. Um, we needed to define the center of glass U value criteria, center of glass solar heat gain coefficient criteria for the project, which basically was compatible with the energy model that Atelier 10 was developing. Um, what sort of IGU spacer we would want, what sort of low E coating we would want, what is the color of the low E coating, primary seal color, the secondary seal. As we understand in insulated glazing, there's a primary seal at the spacer, and beyond that, there's a secondary seal, and then safety glass on the inside. For most part, I think most of these properties, as you can see, is all dependent on that one marble, because the coloration of the marble would define what coloration of the low coating we would want. So the marble still exists here. The choice that we had made, or the tried to make, distilling through the initial selection process, affects everything downstream here. The selection criteria allowed us to zero in on the low coating type. We were able to define center of glass performance. We were able to define what the spacer type would be, what the edge frit color could be, and also the interior lighting calibration, because there's a big change. If you switch the light temperature, for instance, how the experience of the stone is drastically altered. So that sort of calibration also took place with that particular stone and within a IGU assembly. Speaking of the color calibration, we did a quick chromaticity study of all the low iron glass and the alloy coating. We knew that the stone would give us a lot of benefit in solar heat gain, but we needed a U value. For that, I think we mapped up all the low coatings, which are very close to the low iron glass as much as possible. So we were able to shortlist some of these low coatings or solar coating, which were very close to the low iron glass in coloration. So this was a color check based on that. This project, like few other projects that we done, deployed something called a pre-award mockup, which is really, it's a mockup, a visual mockup or a full-scale mockup, which happens before the tender actually goes out, which allows the design team, the owner, to evaluate what's available out there as a material and really test it out. We were able to sort of get this before the actual project was awarded to the facade contractor. But we were able to invite and collaborate with 6 other stone glass suppliers and quarries to get 6 options on the table, which actually matched or tried to match the initial design intent. The image on the right sort of gives you that coloration variance as you change the temperature of the lighting. That allowed the lighting consultant, that was Susan Tillotson, to calibrate the interior lighting that they're using to a level that was deemed ideal for that particular stone. What it also did was, these were not just one stone. We were sort of testing out multiple stone types, and each stone type has its own coloration, vein density, the vein profile. So that really was a very helpful sort of in the process to actually have this and have this tested at that scale. And we take one more step closer to going from stone to stone glass laminate. Now we are in insulated glazing world. Uh, we are now actually at the curtain wall level, where we are looking at the actual system design, how the stone that went from stone to stone glass laminate to a stone glass IGU gets incorporated into a curtain wall system, which can then hang onto the building. So the criteria, like for any curtain wall, this was basically looking at the wind load requirements, the snow load requirements, this nice seismic event, the impact and live flow deflections of the roof, maintenance requirement, how this facade is going to be maintained, thermal expansion and contraction, looking at that, thermal performance for the assembly curtain wall unit, the fabrication, how are we going from stone to actual curtain wall, installation of each of these units, blast criteria given the site. Most of these buildings have a blast criteria. There's a water barrier for any curtain wall unit. We needed to keep the water ingress to zero. What is the air infiltration? It's doubled up here. Then the last criteria was the condensation resistance. And what it allowed us to do was to define a curtain wall performance that we can achieve. That became part of our specifications in the tender document. It allowed us to define what performance mockup testing we would need for this curtain wall, and what is the actual facade system design. What are the details at the top, at the base, at the slab, how they actually terminate at each ends. It also allowed us to define what the visual mockup would require to be. Some images of our analysis. On the left is this particular slide is for thermal analysis. I could not add more than this, but I think this is just gives you the typical condition in plan on the left and in section on the right. The general concept here is, if you see the image on the left, is what it is going to be eventually. It's a long span steel sort of a structure that will get hung from the top all the way down to this plinth level, the total height being about 120 feet. The largest span is about 70 feet. This is the representation of that span. There is no horizontal framing, so the glass or IGU spans from one steel column to the other column. Some other additional our typical structural analysis that we did, the glass deflection and stress on the left, and the deflection and stress analysis for the steel hanging columns there. Just to recap, this whole process, starting from the quarry on the top right, if you follow the arrows across, the quarry generates the block. This is a process that we would see, or we are seeing currently. So the quarry generates the block, cuts that block into slabs, and then the slab is then photographed and sent to Rex for analysis. So they give their feedback, and that particular slab is then cut. There's a certain few additional steps here because as we selected the stone, which is now coming from Portugal, because of the structural capacity of the mechanical property of the stone that was selected, it needed to be impregnated with epoxy to make it viable for it to be transported from the stone quarry and the stone fabricator to Germany from Portugal, where it is being processed into a glass laminate. And at the glass end, each tile is then sort of heat soaked, which is basically baking the stone in the oven to evaporate all the epoxy that is there and evaporate all the moisture that could be there before the stone lamination is undertaken. At that point, each of the stone and glass laminate is then photographed in frontlit and in backlit condition, which is then basically uploaded to a central database with its unique ID. And the software that I was talking about previously looks into that database and populates the facade based on those properties, which is then basically goes back to Rex for their further evaluation and design tweaking. There's a dry lay also in place. Eventually, portions of this facade will be dry laid and tested visually. You could see the stone glass lamination happening and then going to stone glass IGU. All along this process from the stone tile to the actual IGU, each of these steps are being tagged and each of these units are being tagged. And once the IGU is fabricated, uh, the aluminum subframing or the cassettes are bonded to the back end of this IGU, which creates the curtain wall units. And that unit is then shipped from currently being produced in Germany, which is now getting shipped to the site here in New York. One thing that as a system design approach, just to recap, the initial grain of the tile, the way it was decided, we knew that it was marble. We knew it will be a softer stone. So from the very onset, we defined that size. With that, we sort of specified a size of 5 feet by 3 feet, which is a very reasonable size for a marble slab. And that became the actual curtain wall unit size. So even the granularity and the panelization is uh, is driven by the stone itself. And but creating a smaller 5 by 3 panel compared to more conventional curtain wall units, it would have created a lot more units to install in place. So what we went in is to with an intent to reduce the site engagement and installation time. We proposed a system where we take 4 panels in a column together and gang them in as a mega panel, and which will then get installed in site. So we would be cutting down on that installation time substantially. Um, Rough in the diamond, another piece or snippet from Josh's initial design concept. The way the project was envisioned, it needed to be very sort of somber on the outside, very sophisticated on the outside, given the siting. But on the inside, I think the intent was to push the limit as much as possible to make it grow a bit more rough, to represent the amount of energy that they are anticipating with the creative sort of agencies that the people or the people who are going to use that space will have. So it was supposed to be compatible, and he wanted to represent that vitality and that energy on the facade itself. How you can actually make it a little bit more rough, a little bit more sort of uh, non-refined, sort of always on the move, that allowed an easy reinterpretation of the space continuously. If you dig deep into this project, I think one of the sort of a unique selling point of this project is this reconfigurability of the interior space based on what that use is going to be. And I think the intent was not to have a well-defined and very clean and sophisticated on the inside, but a little bit more industrial, a little bit more rough, that is up for reinterpretation. I think that was just the sort of a gist of what the intent was looking at. Um, just a quick sort of check on where we started. This is no longer the kind of the space that we have in the project. This is no longer the kind of facade we have in the project. But this is where it started, this sort of the ambition to take a vibrant and sort of a transformative facade, and figure out a material that can do that and take that material all the way to actual installation. This is where we are currently, and this is the intent of what it would be like. And this is looking at what the veining and the coloration of each stone panel is currently. Some more images. This is looking a little closer to the building. As you approach the building, the lower portion is clad in granite, sort of honed, matte finish. And there's a grand staircase that takes you up to the entrance. On the left is a tunnel, which doubles up as a VIP entrance, or anybody with special needs who can actually use that instead of climbing up the staircase. And there's an elevator that takes you to the entrance level. View on the interiors. Rockwell Group is managing the interiors and designing that. But you could see the actual facade getting a little bit closer to real, what it would look like. This is the current condition at site. The steel structure or the superstructure is almost up all the way up, and it's waiting for the first install of the curtain wall, which will happen sometime in June or August. This is an image from Gartner, and you could see the curtain wall unit being produced in Germany currently. And I wanted to sort of take a pause and circle back on these two initial images and sort of re-stress the initial thought that I had was the idea of innovation and where and in which industry is open to a sort of a queue for innovation, and then from where and then from which direction, depending on where we are. I think all industries are striving for innovation. So I think it's good to understand there is continuous progress that is being made. The aviation industry is creating more and more innovative materials every day. So is architectural industry. But the cues are slightly different. And I think the cue starts with the design and the choices that a designer makes with each of those projects that really kind of pushes the boundary of what is feasible and what has been undertaken so far, and really creates something new and something worthwhile. So just wanted to flag these two images together just to reiterate what I started this presentation with. And with that, I think that is the end of this presentation. Just a quick note, I don't know if I think Daniel did a fantastic job introducing me in front. In general, I think we started in 2002, and we are about to sort of close in on about 300 projects so far all over the world. These are each dot represents a project that we have touched. We are operating out of 6 different offices, 3 in United States, in New York, San Francisco, and Seattle. There's one in London, one in Verona in Italy, and then one in Hong Kong. And yeah, and just wanted to stress again how I'm very grateful for this opportunity to actually show some of the projects that we have been working on. And also thankful to Daniel to invite me to his studio.